A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. What if your AI agent could actually get smarter at runtime without a single weight being updated? I mean, we all know the deal. You download a model, it's a static blob of math, and that is what you are stuck with until the next version drops. But there is a massive gap between a static model and a dynamic agentic system.
It is the ultimate paradox of modern AI. My name is Herman Poppleberry, and today we are looking at how the harness, the environment, the tools, and the feedback loops can actually steer a frozen model into performing like a much more capable, evolving entity. Today's prompt from Daniel is about reinforcement learning in agentic AI, specifically looking at a project called OpenClaw-RL.
And just a quick heads up for everyone listening, today's episode is actually being powered by Google Gemini 3 Flash. So, Herman, Daniel is pointing us toward this OpenClaw-RL project on GitHub by the Genverse team. It seems to be tackling this exact problem. How do you take a model that is technically done and make it better through interaction?
Well, not exactly in the sense of a permanent fix, but exactly in the sense of the challenge. See, when we talk about LLMs, we are talking about a snapshot. It is a statistical map of language frozen in time. But an agent is a process. It's a loop. You have the model, sure, but you also have the memory, the tool use capability, and the environment it is interacting with. OpenClaw-RL is fascinating because it treats the agent as a dynamic participant in a continuous feedback loop rather than just a text predictor.
Right. So even if the weights of the model are a static artifact, the way those weights are utilized can be shifted. It's like having a driver who knows how to drive, but you're changing the car, the GPS, and the road conditions in real time to make them a better racer.
That is a decent way to look at it. In the context of OpenClaw-RL, they are using reinforcement learning, or RL, not just for the initial training at the factory, but as a way to shape behavior in the wild. Normally, RL is this heavy, offline process. You run millions of simulations, you calculate gradients, and you update the model. But OpenClaw-RL is pushing this idea of online RL, or asynchronous RL. It's basically saying, while the agent is talking to you or clicking around a GUI, we are collecting data in the background to refine how it handles those specific tasks.
Okay, let's break down that loop because I think that's where the magic happens. If I'm using an agent to, say, automate my desktop through a GUI, which is one of the big use cases for OpenClaw, how does RL actually teach it if the model itself isn't changing its brain in that exact second?
So, the OpenClaw-RL architecture is built on a 4-component loop that runs in parallel. First, you have the agent serving. This is the model acting as an API. It takes a screenshot of your screen, looks at the buttons, and decides to click Submit. Second, you have Rollout Collection. The system is essentially recording every trajectory, the screenshot, the thought process, the action taken, and the result.
Like a flight data recorder.
Precisely. Third, you have the evaluation. This is where it gets technical. They use something called a process reward model, or a PRM, or sometimes just a judge model. This evaluator looks at the trajectory and says, did clicking submits actually move us closer to the goal, or did it just open a random help menu? It assigns a reward signal. And finally, the fourth part is the policy training. This happens in the background. It takes those rewards and uses an optimization method, like PPO, which stands for Proximal Policy Optimization, to update a version of the model.
So it is eventually updating weights, but it's doing it in a way that feels like it's learning from the harness of the environment.
Yes, and that is a key distinction. In a standard chatbot, there is no environment. There is just text in, text out. In an agentic context, the environment provides the ground truth. If the agent tries to run a shell command and gets a command not found error, that is an objective mathematical signal that the action failed. You don't need a human to tell the model it messed up, the terminal just did. OpenClaw-RL leverages that exit code as a reward signal.
I love that. It turns the harness into the teacher. But I want to dig into the levers we have before we even get to the weight updates. Because for a lot of developers, they can't afford to run a full RL training loop every night. What can we do with just the system design to mimic that kind of improvement?
This is where the agentic context becomes the primary lever. Think about memory. If an agent has a short-term memory of the last 10 failures, it can use that context to change its next move. That isn't learning in the biological sense, but it is a behavior shift. OpenClaw uses what they call hindsight hints.
Hindsight hints? That sounds like what I give myself every Monday morning. I should not have stayed up that late.
It's surprisingly similar. In their on-policy distillation method, if an agent fails a task, a teacher model, usually a larger, more expensive model, looks at the failure and generates a hint like, you should have checked the file permissions before trying to write to that directory. That hint is then injected into the prompt for the next attempt. The frozen model now has new information in its context window that effectively patches its behavior.
So the harness is essentially acting as a real-time editor for the model's intent. But what about tool routing? That feels like a huge lever. If the agent has a toolbox, the way it chooses those tools is really what defines its intelligence in the real world.
Tool routing is arguably more important than the raw reasoning of the model for most practical tasks. In the OpenClaw ecosystem, they have this skill bridge. The RL process can be used to optimize the sequencing of tools. For example, if an agent is trying to fix a bug, it might have a search tool and a edit tool. A naive model might search, then edit, then search again. But through RL, the system learns that searching twice before editing leads to a higher success rate. It starts to internalize that sequence, not because the model changed its fundamental understanding of code, but because the reward signal favored that specific trajectory.
It's like building a habit. But let's get into the weeds of the rewards themselves. You mentioned process reward models. Most people are familiar with outcome rewards. You win the game, you get a point. But in a complex agentic task, like a software engineering agent trying to refactor a whole repo, the outcome might be 20 minutes away. How do you reward the small steps?
That is the reward sparsity problem, and it is the bane of RL developers. If you only give a reward at the very end, the model has no idea which of the 50 steps it took was the one that actually mattered. Did it succeed because of the clever regex it wrote at step 5, or despite of it? Process reward models, or PRMs, try to solve this by scoring every single step. They look at the thought the model had and the action it took and give it a mini-score.
That sounds prone to reward hacking, though. Couldn't the model just learn to say things that sound like good steps to the PRM without actually making progress?
Oh, absolutely. Reward hacking is a massive risk. An agent might learn that the PRM loves it when it verifies the environment, so it just spends the whole time running ELStree and ELStree and ELStree over and over again to rack up many points without ever actually writing a line of code. This is why OpenClaw-RL is so interesting. They try to balance these PRMs with binary rewards from the environment. The terminal exit code doesn't care how smart you sounded, it only cares if the file exists.
I think that's a really important point for anyone building these systems. You can't just rely on another LLM to be the judge, because then you just have two models hallucinating in a circle. You need that objective anchor in the harness.
And the harness can be even more than just the terminal. Think about GUI automation. OpenClaw-RL can train an agent to interact with a pixel-based interface. The reward, there might be the change in the pixel state. If the goal is to open the settings menu and the agent clicks a spot that causes the settings menu to appear, the vision model can verify that state change as a positive reward. It's very grounded.
So, we've got memory, tool sequences, and environmental rewards. What about the levers that are more about the data itself? Daniel's notes mentioned group optimization. That sounds like something that would be relevant for enterprise teams.
Group optimization is a very recent milestone, actually just from this week. It allows a single model to be optimized based on feedback from a whole group of different users simultaneously. Imagine a team of 10 engineers all using the same coding agent. One engineer likes concise code, another likes heavy documentation. Group RL can start to shape the policy of the model to find the optimal middle ground that satisfies the most users, or even branch out into personalized profiles. Again, you aren't retraining the whole model from scratch. You are using the RL harness to tilt the model's existing capabilities toward a specific style.
It's like a democratic fine-tuning process that happens while you work. But let's talk about the limits. We've been painting a very rosy picture of frozen models getting smarter, but there has to be a ceiling. I mean, if I have a really small, weak model, no amount of RL in the harness is going to make it write a Shakespearean play in C++, right?
You hit on the static artifact problem. At the end of the day, an LLM can only output tokens that are within its probability space. If the model literally doesn't know how a specific library works because it was trained before that library existed, RL can't hallucinate that knowledge into existence. It can help the model navigate the documentation for that library more efficiently, but the core reasoning capacity is still capped by the original pre-training.
Right. It's the difference between a better strategy and more raw brain power. You can give a middle schooler the best chess coach in the world, and they'll get much better, but they still might not beat a grandmaster who just has a deeper fundamental grasp of the game.
And there's also the hardware friction. Running this OpenClaw-RL stack isn't exactly light. To do full asynchronous training, you usually need a serious GPU cluster. We're talking 8x H100s for the big stuff. Now, they have introduced LoRa support, low-rank adaptation, which makes it possible on single GPU setups, but is still a lot of moving parts. You have a server for the model, a database for the trajectories, a separate model for the evaluator. It's a high-complexity architecture.
And let's not forget the data privacy aspect. If the system is learning from every conversation to update its weights in the background, is it accidentally memorizing my API keys or my son Ezra's birthday?
That is a legitimate concern. When a model undergoes RL or fine-tuning on live data, there is a risk of weight poisoning or just unintended memorization. If you tell the agent, my password is I love donkeys, 123s, and then the RL loop decides that was a very successful interaction, those tokens get reinforced. Future users might find the model suggesting that exact string. OpenClaw-RL tries to mitigate this by filtering trajectories, but it's an ongoing challenge in the field of agentic safety.
I love donkeys 123. Is that actually your password, Herman? Because that would be very on brand.
I will neither confirm nor deny the donkey-related nature of my security protocols, Corn. But moving back to the system levers, one of the most interesting ones is the teacher-student distillation.
Lay that out for me. Because if the teacher is just another model, why not just use the teacher all the time?
Cost and latency. This is the fundamental trade-off of 2026. You want the intelligence of a trillion parameter model, but you want the speed and price of a 10 billion parameter model. In OpenClaw-RL, the teacher model, maybe something like a massive Claude or Gemini model, is used to provide those hindsight hints I mentioned. It looks at what the student, the smaller, faster model did, analyzes the mistake, and says, here is exactly what went wrong. The student then learns from that high-quality feedback. Over time, the student's weights are updated through RL to mimic the teacher's reasoning process for those specific tasks.
Ah, so you're using the harness to bridge the gap between cheap and fast, and expensive and smart. That's a massive win for anyone trying to build a production-grade agent.
It's the only way to scale. If every single step of a coding agent costs 50 cents in API fees, it's not a viable product. But if you can use that 50-cent model to train a 1-cent model on your specific code base, suddenly you have something powerful.
So looking at the OpenClaw-RL repo specifically, what is the state of the art right now? They mentioned something called binary RL versus on-policy distillation.
The current sweet spot in the repo is a combined method. They use binary rewards, did the task succeed or fail to give a high-level signal, and then they layer on the token-level hints from the distillation. This gives the model both a goal and a path. If you just give it the goal, it might take 1,000,000 tries to find the path. If you just give it the path, it might follow it blindly without understanding the goal. by combining them, you get an agent that is much more robust.
It's like teaching someone to bake. You can show them a picture of a perfect cake, the goal. But you also need to give them the recipe and tell them why their first cake was flat, the hints.
And what's wild is the performance data Daniel sent over. In their evaluations, OpenClaw-RL showed visible improvement in just 24 to 36 interactions. That is incredibly fast. Most people think of AI training as something that takes weeks and billions of data points. But when you are working in a constrained, agentic context like, how do I use this specific internal database tool, the model doesn't need to learn a new language, it just needs to learn a new policy.
24 interactions? I've had arguments with you that lasted longer than 24 interactions, and you still haven't improved your policy on where we should go for lunch.
That's because my reward function for tacos is set to infinity, Corn. There is no counter signal strong enough to break that. But in all seriousness, that speed of adaptation is what makes this harness-first approach so compelling. For a developer, it means you don't have to wait for the next frontier model to solve your problem. You can start shaping the behavior of the models you have today.
So, if we're looking at the broader implications here, it feels like the harness is becoming the new frontier of AI innovation. People used to obsess over the architecture of the transformer itself, how many heads, what kind of attention. But now, the focus is shifting to how do we build the best environment for this transformer to live in?
I think that is the most profound takeaway from the OpenClaw project. The model is just the engine. The harness is the transmission, the wheels, the sensors, and the driver's seat. You can have a Ferrari engine, but if you put it in a lawnmower frame with no steering wheel, you aren't going anywhere fast.
And a lot of AI agents today are basically Ferrari engines, strapped to lawnmowers. They have all this raw reasoning power, but they are constantly crashing, because their memory is messy, their tool calling is buggy, and they have no way to learn from their mistakes.
Right, and the RL in the harness approach gives us a way to build that steering wheel. It's about creating a system that is self-correcting. One of the things I found really interesting in the technical report was how they handle session-aware trajectories. They actually classify messages into mainline actions, things the agent did and side turns like the agent asking the user, hey, what folder did you want me to look in? They only optimize the mainline actions.
That's smart. You don't want to reinforce the agent's tendency to ask clarifying questions, as if that's the goal. You want to reinforce the result of the action it took after getting the answer.
It's about isolating the decision-making logic from the conversational filler. That kind of nuance is only possible when you are building at the harness level. You can't really do that through traditional pre-training.
So, let's talk about the practical takeaways for someone listening who is, say, a developer or a technical lead. If they want to start shaping behavior without waiting for a new model, where do they start?
The first step is to define your environment as a Markov decision process. That sounds fancy, but it just means define what state the agent is in, what actions it can take, and what rewards it gets. If you are building a coding assistant, the state is the current file, the action is a git commit, and the reward is the test suite passing. If you don't have a clear reward signal, RL can't help you.
So, step 0 is build a better test.
Always. If you can't measure success programmatically, you can't automate improvement. Second, look at your memory architecture. Are you just dumping everything into a long context window, or are you using hindsight hints? If an agent fails, don't just clear the chat and start over. Save that failure, have a larger model explain why it failed, and put that explanation into the long-term memory for that specific task. That is a form of frozen model improvement that you can implement today.
And third, I'd say, experiment with these open source frameworks like OpenClaw-RL. Even if you don't run the full RL loop, just looking at how they structure their trajectories and their skill bridge will give you a much better mental model for how to build a robust agent. It's about moving away from prompting and moving towards system design.
Well said. Prompt engineering is like giving someone a very detailed set of instructions. System design is like building a workshop where it's impossible for them to pick up the wrong tool. One is fragile, the other is resilient.
I like that. Prompting is instructions, system design is the workshop. I'm going to steal that for my next blog post.
You're welcome. But we have to acknowledge that there are still some major unsolved areas. One of the biggest is long horizon reasoning. Even with the best RL harness, agents still tend to drift when a task takes more than, say, 50 or 100 steps. They get lost in the weeds.
Is that because the reward signal gets too diluted over time?
Partly. It's also just the accumulation of error. If an agent has a 99% success rate at each step, but the task requires 100 steps, its chance of overall success is only about 36%. RL can push that 99 to a 99.9, which helps, but it doesn't solve the fundamental entropy of long chain reasoning.
That's where we might hit the ceiling of what a static artifact can do. Maybe at some point, you do need a model that can fundamentally rewire its own logic, rather than just its policy.
That is the big open question. Will we see truly continuous learning models that update their base weights with every single token? There is research into things like fast weights or hypernetworks that could do this, but they are still very experimental. For now, the OpenClaw approach, the asynchronous, harness-based RL, is the most practical path forward.
It's the good enough solution that actually works in production, which, in the tech world, is usually the one that wins.
And it's worth noting that this isn't just for coding or GUIs. Think about scientific discovery agents. You could have an agent that proposes chemical experiments. The harness is the lab equipment. The reward is the yield of the reaction. The agent learns which experiments are wasteful and which are promising based on the physical reality of the lab. That is a massive shift from just summarizing papers.
It turns the AI into a partner in the physical world. I mean, we're seeing this with robotics too, right? End-to-end RL for robot arms is basically the same concept. The harness is the physical sensor data.
It's all converging. Whether the body of the agent is a robot arm, a terminal window, or a web browser, the principle is the same. Use the environment to ground the model's reasoning. And as Daniel's notes pointed out, we are seeing visible improvement in 24 to 36 interactions. That is the metric I want people to walk away with. You don't need a year of data. You need a weekend of high-quality interactions.
A weekend of high-quality interactions. That sounds like a very productive retreat. So, to wrap this part up, we've got the frozen model, which is our engine. We've got the harness, which is our workshop. And we've got RL, which is the process of the engine learning how to use the workshop more effectively.
And the beauty of the OpenClaw-RL project is that it's all open source. You can go to GitHub right now, look at the Genverse repo, and see the code for the evaluator, the rollout collector, and the policy trainer. It's a blueprint for the next generation of AI systems.
It's definitely a weird prompt topic, but honestly, it feels like one of the most important things we've talked about lately. It moves the conversation away from, is AI going to take my job, to, how do I build an AI that actually works for my specific job?
That is the shift from generative AI to agentic AI, from making things to doing things. And doing things requires a feedback loop.
Well, I'm convinced. I'm going to go home and build a reward function for my coffee machine so it learns exactly how much cream I like through reinforcement learning.
Corn, I think a simple if-then statement would suffice for your coffee. You don't need a GPU cluster to avoid a bit of milk.
Where's the fun in that, Herman? If I can't use proximal policy optimization to get the perfect latte, am I even living in 2026?
Fair point. I suppose I'll just stick to my donkey-themed security protocols and let you handle the high-tech caffeine.
So, looking ahead, what's the next big milestone for this kind of harness-based RL? Is it going to be more about efficiency or more about multi-agent cooperation?
I think it's both. We're already seeing multi-agent RL where different agents, say, a coder and a reviewer, are optimized together. The reward for the coder is the reviewer's approval, and the reward for the reviewer is the final code passing the tests. They start to develop a language of cooperation that is optimized for the specific task. That is where it gets really weird and really powerful.
It's like a tiny digital corporation where everyone is perfectly aligned toward a single goal. No office politics, just reward signals.
If only humans were that easy to optimize, Corn, we'd have a lot fewer meetings.
I don't know. I think my side turn frequency in meetings is a very important part of my charm. You can't RL that out of me.
I think the judge model would give you a 0 for meeting efficiency, but a 10 for brotherly entertainment.
I'll take it. All right. I think we've thoroughly dissected the harness. It's been a deep dive, but a necessary one. The takeaway for me is, don't blame the model for being static. If your system design is stagnant, use the tools, use the memory, and for heaven's sake, give your agent a good reward signal.
And if you haven't checked out OpenClaw-RL, go give it a star on GitHub. It's a project that is really pushing the boundaries of what user-hosted AI can do.
Thanks for the deep dive, Herman. You really donkeyed your way through those technical details today.
I'm going to assume that's a compliment on my persistence and not a comment on my stubbornness.
Why not both?
This has been My Weird Prompts. Thanks as always to our producer, Hilbert Flumingtop, for keeping the gears turning behind the scenes.
And a big thanks to Modal for providing the GPU credits that power this show, including the ones used for our script generation today.
If you're enjoying these deep dives, a quick review on your podcast app really helps us reach new listeners who are looking for more than just surface-level AI news.
You can find us at myweirdprompts.com for the RSS feed and all the ways to subscribe. We'll be back next time with another prompt from Daniel.
Until then, keep experimenting with your own agentic harnesses.
And maybe don't use "I love donkeys" as your password. Just a thought.
Goodbye, everyone.
See ya. This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow take